Fine. So let's start. So we we proposed two implementations of the union find data structure in the last class or last meeting. One is requiring, the first one is the union operation is actually linear, whereas the find is constant. So this is the array implementation where the union is the find operation is linear, as you can see, constant time, and the union operation is linear, this one. And the second implementation, which is based on the linked list, we used linked list, and we used a special kind of union where the smaller units actually changes its name. The bigger component keeps the name. Uh, in that way, we can make the union a constant operation. Union is constant operation, okay, order one operations, whereas find actually may lead to the actually order of log n, where h is equal to log n by that special operation. So this is really nice. So one thing we should add at this moment that will help you to understand the situation better. So let us now think about what happens to in this linked list kind of implementation of union find. So let's say the structure of the graph, structure of the tree at any point of time is like this. Okay, so these are all the connections. I mean, additional structure I maintain to check the union find. I mean, when a new see, this is not the this is just a data structure uh, to to help us implement the Kruskal's algorithm. I mean, we check whether an edge creates a cycle or not. Because if we know that there is an edge, which is the next edge to be inserted, and the edge is uv, the edge is of the form u comma v, and if I call find u and find v, they returns the name of the respective components, and if they're equal, then they belong to the same component. That means there is already one path between them, and I'm going to add another path. So this is going to create a cycle. So that is the main purpose of this. Now, uh, what happens? Let's say this is the intermediate structure. Up to this point, the union has happened. It is because of the unions that the structure looks like this. Okay. So now let's say there are some other vertex here. Okay. Some other component here. Okay. And there is also an edge here. I mean, this edge is not an edge in the structure. It is actually an edge in the original graph. And let's say this is U1, this is U2, suppose. Now, what will happen? We will consider the edge U1, U2, because that is next stage in the sorted list. So we take the edge and we check find U1 and find U2, and then we check whether they're equal or not. So see, find, how do I know find U1? Find U1 will actually check in its own component, which is maybe around here. And find U2 will check its own name, the name of the component containing U2, and which is also around here. is this component, and it will actually check here and then go here, and then it will return, right? So worst case, I can say this will require login, this will require login, something like that. Now suppose after this operation, what happens? I see that there is another age that is in this list. That is, let's say this is I mean U3, and this is, let's say, U3 dash, let's say. So, and let's say there is an age like this in the original graph. So let's say there is an age U3 dash. Now what I will do, I will just do the same thing. Okay, I will compute find U1, and I'll compute find U3, and I'll compute find U3 prime, and then I'll check whether they are equal or not. Okay, like that. If they are not equal, then basically I will try to make union, and how the union will happen, this will basically point to the root here, something like that. But one thing we must notice in this case is that, so first, my question was, what is the value of find U2? And the second case, I had a question, what is the value of find U3? Even though from the picture, it is evident that both belong to the same component. And if I once know the name of this tree, then I should actually know the name of any node in this path. I should know the name of any node. I mean, the name of the component for any node in this path is actually the same. It should happen. But due to this way of organizing the structure, it is, and every time actually unnecessarily we are calculating find U3 prime like this, even though it is not required, because I already know. So what is the logic? The logic is, if I once know the name of the component of a particular node in a particular component, then any node in that path from the leaf to the root, every node, I can actually I mean, I know that the name is same for everyone. Actually, in every element in this subtree, actually, it is like that. So how to do that? Okay. So what we do is we utilize this concept. We utilize this concept. So what is done? So let's just take a clear example that will make it better. Okay, let's say this is the name of the component, and this is the data structure, union find data structure tree. And let's say this is my V. Okay, and I somehow, and there is some other node U here. Okay, and I actually did the find U find V. So what I can do is, after that find V, I know this. What I can do for this, let's say this is the parent node P. So what I can do for every node in the, for every node in the path from P to V, P is the root node, after which there is no further way we can go up. So for every node in the path from P to V, what we can do, we can reset the pointer directly to the root. We can reset the pointer directly to the root. What does it mean? That means this connection is this node actually it is directly attached to the root node. Okay, that's fine. I'm not doing any change in the node in the nodes in the left. Okay, what will happen for every node like this node? I'll make the connection direct. So what I'll do, I'll delete this and I will make this. I'll make it point directly to this. For this node, I will just remove this and I will make the connection direct to this. Okay. I'll make a direct connection to the root node. So what will happen then? See, how I have two things to consider now. One is how much time I take to do this. And the second thing, what benefit do I get out of it? Okay. So the direct, how much time it takes to do the direct connection? Let's say I did this find V once. Okay. So I traveled this entire path, V to U, V to P. Okay. And that's why it took log n time. And when I try to reset these connections direct to the root node, I again travel another log n. Okay. So it results in actually 2 times the find V. 2 times the find. Nothing more than that. 2 times because the same path I just reset. So once I actually check the root until I reach null, and the second case I actually reset the pointer straight to the root. Okay. So 2 times I traverse this path. So I need 2 times. But what good I get is after this operation, if any further find operation, find x like operation comes due to any edge like x comma y in the sorted list, then this x happens to be some node in this path. Okay. Okay. You p to v path. If x belongs to any node in this p to v path, then in that case, find of x actually takes constant amount of time. Because just by one step, I can know the name of the component. So that essentially means initially for the first time I am doing find v for a particular v, instead of just doing it once, I will do it 2 times. Okay. Just to make this resetting of this pointers. And every later time, any such find operations comes for any node in that path, it will require constant amount of time instead of log n amount of time. Because if I did not set this like this, then the operation would take log n amount of time. But now since I am making them direct to the root, because in one hop I can tell the name of the component, therefore it is actually constant amount of time. So this is a special kind of arrangement, which is often called uh, uh, path compression technique. This technique is known as path compression. Okay, so union find data structure implementation using linked list and using path compression. What is the method of path compression? I mean, for every find operation, the union operation is very simple. I just I just put a link actually direct. It's just like this one, just like the same union operation. Union operation I do not choose. Union operation is like this. Whereas find operation, so instead of a single find, I do two finds. If I see the length is too much, length is more than one. Okay. So this is known as path compression technique. So what benefit do I get? We so so in this case, as you can see that the union operation is constant time, but the find operation, it may appear to be that the worst case is still log n, because first time I do a find, it does 2 times find v, okay? And that one find v is essentially one time it does is log n, okay? So this is 2 times log, but that is worst case. So if you do worst case analysis, then it is still log n, okay? It is still log n. But sometimes a better analysis can be done, which we will see later in many places, which is known as amortized analysis. Amortized analysis. So what is the idea? The idea of the amortized analysis, let us say that an application requires n find operations. Let us say an application requires n find operations. Let us assume this is some parameter. Now, it is not, it may so happen that one or two of them may require log n, okay? But if rest other all require constant amount of time, then you can do really some better calculation, okay? What we do is the first, see here you cannot just say that let us number the find operation. Let's say the first, second find and etc. up to nth find operation. You really do not know how much find which of these nth find operation is going to take, because it depends on the exact graph structure. Because if you think all are disconnected components initially, then first few finds actually will anyway require small amount of time, because the height of the tree in that case is, or the tree has not yet been formed, right? So most of the cases it will be, let's say, constant operations, okay? And then after the size of the individual trees become of the order of say n size, I mean the height becomes of the order of log n, then if any kind of initial find may result in log n operations, and then maybe a large number of subsequent find operations will almost require constant operations. And then again, in some part, it may require log n operations, and then subsequent things will be constant operations. So it can be argued that out of n such find operations, only few are log n, and most of them are actually constant. Okay. So what is the amortized analysis? Idea amortized analysis is you sum up all these, okay? Let's say cost of ith find operation, and then you average it over all the ith operation. Okay. Now let's say it, let us say that okay, a constant number of such find operation. I mean, constant number of such finds are actually log n. So I can write it like this: 1 by n into some constant c1 into log n plus if this is constant, then this is n minus that constant into constant time, order one time, let's say. So this comes to be log n by n plus this is actually something like you can say linear. This is constant. Okay. So this is although this is a very I mean I mean loose analysis, I will say, with the assumption that I assume that there are constant number of these log n operations, and there are a total of n operations, n such find operations. Okay, so there is a general result which we will just state that. So it can be actually, I mean, it can be shown that the just a minute, class. It can be found that for a sequence of n find operations, the total time, okay, the total time when we use path compression of n finds, the total time when we use path of n finds, that is actually of the order of n times some alpha n. Okay, n times some alpha n. What is this alpha? This is something known as inverse Ackermann's function. Okay, and for very large values of n, okay, let's say very large, let's say 2 to the power of 2 to the power of 2 to the power of blah blah up to say n. Even for very large values of this, if this n corresponds to this thing, this very large value, even then it can be shown that this Ackermann function returns a value something less than 10. Okay, something less than 10. So for most of the practical purposes, it can be shown that this value of this Ackermann's function return for arbitrary large value of n, you can say very large value of n, exponentially large values of n. Even in that case, these Ackermann functions returns a very small constant, which is strictly smaller than 10. So overall, you can think of this is approximately, you can say, some order of n. Okay, so for a sequence of n find operations, the total time, okay, will be order of n if you use path compression. Okay, and what is the average time in that case? Average time. Remember, this average is not, I mean, a random average. It's not a average associated with some probability. It's actually sum up all the individual operation times, and then you do the average. The average will be roughly this, which is roughly constant. Okay, for most of the practical values of, okay. So if you use Ackermann, this path compression technique, okay, then the union remains, so we can write that with path compression, and linked list representation. Find is roughly order of 1. Union is roughly order of 1. Okay, so both the operations are actually roughly order of 1, which is very appreciable. So so what is the, so this is the thing you should understand, that and this is the union find data structure, and each operation takes roughly this much amount of time. Now another question lies, does this improve the complexity of the Kruskal's algorithm? Okay, so if you remember, what is the procedure of Kruskal's algorithm? The procedure is you sort all the edges in increasing order of their weights, and then you take the minimum cost edge, okay, and then you check whether find u and find, if uv is that edge, then you check find u and find v using this union find data structure. If find u is equal to find v, then you do not add that edge. If find u not equal to find v, then you do add that edge in the graph. Okay, and this process you repeat for until all the edges are exhausted. Okay, so if you try to analyze the complexity, the sorting of all the edges, okay, this requires order of m times log m. Okay, when m is the number of edges, so you know that m is actually in the worst case roughly n square. Okay. Oh. So you can say that this is roughly n square. So you can see that this is roughly m into log of n square. So this is actually roughly m log n, because this 2 will come here and this 2 will go into the constant, something like that. Sorting will require m log n time. And after that, it will essentially be depending on the how many union operations and find operations. So it can be shown that there will be, see, there are how many edges? So m edges. So there will be 2 endpoints for every edge. So there will be at most 2m find operations. So that will require twice m, and each find, let's say we use the best union find using path compression. So 2m into constant time that will require, and we will have n minus 1 union operations. Why n minus 1 union operations? Because I will keep on adding edge. Okay, it will become a tree, and as you know, a tree with n nodes has n minus 1. So it will I will be successfully adding up to max n minus 1 edge, and after that I cannot add, because in that case I see that find u and find v return same, so they will result in a cycle. So I can add up to n minus 1 edges. So n minus 1 union operations I do, and that roughly is n minus 1 into constant. So so this means that the overall complexity of the graph of the Kruskal's algorithm is actually, it becomes m log n, basically m log n kind of complexity. So the betterment of the union find actually does not beat the sorting problem, okay, that is required for the Kruskal's algorithm. Then why use union find? Okay, the answer is you see, we do large number of union and find operations. So if sorting can really be done quickly, then now the overall complexity becomes actually this. And this sorting is required only one time. And only this union find can be repeated multiple times actually. So if you process the graph edges in some other way, okay, then this might be helpful. But just them using union find actually does reduce the time complexity too much. Okay, but for some other purpose, it might be useful. Okay, so this is what is more or less all about the union find data structure. Okay, so if anybody has any questions, you can raise. We'll move on to something new. We are so far studying greedy algorithms, and we have studied a couple of topics. I will post in my, I will update my web page. I have not done it. With 1 month has gone by almost, and we have covered a set of topics. Just I'm naming them. If you have any, if you disagree, then let me know. We have done the stable matching problem, okay, and then we have done interval scheduling problem with single resource, then accepting all intervals under multiple resource, that we have just asked that, okay, I mean, there is a way modification of that algorithm, you can read the book. And then interval scheduling with single resource to minimize the maximum lateness, okay, that thing we have covered. Then Dijkstra's single source shortest path algorithm to find out the shortest path tree. Then we have moved into the MST, minimum spanning tree problem, where the what is MST we have shown with an example. And then there are many algorithms for MST, but we are primarily concerned into the Kraskos algorithm, which uses this union find data structure. There is an algorithm called Prim's algorithm, which is a variation of the Dijkstra's algorithm. Okay, so that is left for self-study. Then we discussed cart property and cycle property, then reverse delete approach, and then this union find data structure. Okay, there is one more thing that is to be done for this greedy. That there are many things actually, but we leave it for the time being. So one thing I will suggest you to for self study is the Hofmann coding. So Hofmann coding is used for data compression. Okay, so this is again another greedy. I will request you for self study because this is not very difficult. So the idea, just one sentence, I will say there are actually certain words. So we want to actually use the frequency of words or frequency of some numbers or some characters to compress the words, because the frequent used words which are very frequently used, we should use codes of smaller length, and for less frequent words we can use codes with higher length. Okay, so some sort of interesting coding technique we can use based on the frequency. So you basically calculate the frequency of all the words, and then you do a special kind of coding. Okay, so you can, I hope you can do it at home. So if any difficulty later we can take up. Okay, so this Hofmann code is again uh, another kind of greedy algorithm design technique. Okay, so now we are actually moving into something interesting, which is known as divide and conquer. Divide and conquer technique. So I will just ask you one thing, that have you learned any divide and conquer technique for solving any particular problem, like you did in CS 203? So was any, okay, divide and conquer, I see that merge, sort, etc. Has been done. Okay, so that's good. So you know roughly how divide and conquer works. So let me just take one interesting problem which you may or may not have encountered in the divide and conquer paradigm, which is very important, and it has also geometric connections. I try to highlight the problem here. So let's say we have a xy plane. Okay, we have a xy plane, and in that plane we have these points. Okay, we have these points, many multiple points are there. Yes. So everybody has a coordinate, okay, like xi, yi. Okay. Now, if you take any 2 points, okay, like this and this, let's say this is point u1 and point u. So what you do, you join them by a straight line, and then you can actually calculate the distance of this separation. So how it is calculated, you know the standard, right? It's like let's say xi minus xj whole square, yi minus yj whole square, and take the positive. This is the distance between those 2 points, right? So now the question is, so let's say there are n points on the plane. Okay, the question is this: calculate or find the closest pair of points. Closest pair of points. Okay, closest pair of points. That means I have how many points? I have n points. I have to find out that 2 pairs. Okay, let's say these are the 2 pairs. Let's say this is P1, this is P2. I have to find that pair, like Pi, Pj, such that their distance is minimum. Okay. So I believe this problem has not been done in earlier. I believe so. So let us try to solve this problem. And this problem has a little part of divide and conquer. Okay. So what is the basic or naive approach? Okay. What can be naive approach? Naive approach means which is very simple, very easy. So the approach is, so if you consider n points, okay, the simplest approach, okay, simplest approach. See, this approach is the pseudo code, or you can think of the overall idea that should be there in any kind of problem solving. The simplest approach is what? Uh, find all pairs, all pairs, all distinct pairs, distinct pairs. Okay, then find distance between them. And then find the minimum. This is the simplest approach. So find all the distinct pairs. Distinct pairs means there are n points, so I can actually have n choose 2 pairs, isn't it? Distinct pairs. I mean, why I do n choose 2? Because it is actually, the ordering is immaterial. I mean, if you consider 2 points, u1 and u2, and the second case you consider u2 and u1, they are actually same pair, because I mean the distance is is independent of direction, right? So this is the all possible pairs, and find distance between them. We know how to find the distance, the square root mechanism. Okay, xi minus xj square plus yi minus yj whole square. You calculate the distance and find the minimum. What you need to do is you actually can you have all these n choose 2 values, okay, because there are n choose 2 pairs, so you will calculate these distances. So you will have n choose 2 distances, and then you will find, so you will actually scan one by one from left to right, and you actually store the minimum in one particular variable, okay. So just one scan, so it will again require actually n by n choose 2 amount of time. Overall this much amount of time it will take. And calculating this distance actually, again, for one pair it requires constant amount of time. So for so many pairs you can think of, it will take order of this much amount of time. So overall time is actually, you can say, something. N choose 2 is how much? N choose 2 is essentially n into n minus 1 by 2, right? So we just generally write this as order of n square. Okay? So overall time will be, overall time requirement is order of n square. N square time. Okay, so in n square time we can solve this problem. Okay, this is plain and simple. Okay, so now the question is, can we do better? Can we do better than what? Better than n square. Can we do better than this square? This. Okay, that is one intriguing question that we ask. Okay, so 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 to do that, we use one technique called the divide and conquer. Okay, so what kind of divide and conquer? Even before going into the actual algorithm, how we design it, probably I will try to highlight one thing. There is, I mean, there is one general philosophy. Uh, there is something like, let's say we designate the overall problem time. The time required by the overall problem is Tn. Okay, and if we can represent this as 2 times Tn by 2, let's say the idea means we partition this, all these points, into two sets. We make a partitioning of this set of points, roughly half points, roughly half points. So if there are n points, roughly here n by 2 and n by 2 points. Okay. So if we can divide that, and then somehow we calculate the closest pair of points in this region, and somehow we find the closest pair of points for this region. Okay, somehow. Okay. And with that, let's say the closest pair of point here is pi pj, and the closest point here is qi qj, let's say. Now with the pi pj and qi qj in hand, if I can join, I can find the overall closest pair. I mean, I have this closest pair in this region, I have closest pair in this region. Then if I add some function f here, okay, fn, if I add, then if I can find the closest pair of points for the whole set of points, okay, then my problem is done. Okay, this is the idea. Now, as you know, that it is very important. Yeah, anybody has any doubt? So as you know, that this fn is very crucial here. Depending on the value you set to this fn, the tn will have different implications. I mean, Tn will have different value. So if suppose if Fn is actually order of 1, then Tn takes some value. If Fn is of the order of n, Tn has some value. If Fn is of the order of suppose n square, then Tn has something different value. Okay, so there is a general expression. Okay, for this, I mean, you might know that this is called Master's logic, Master's theorem. Okay, which says that it is the expression is something like I mean Tn equal to A Tn by B plus Fn, something like that. Okay, and for particular choice of Fn, you can find different values of Tn. Okay, this is the logic, and there is here A and B are both 2 basically. See, this is my A, this is my B. So the idea is this: I will try to divide the problem into smaller parts, like n by 2 size approximately, and then I will join the individual solution to get the overall solution. And to be very specific, I must say that, see, suppose I have somehow got this closest pair in the smaller region, okay, and in this closest pair in this smaller region, then this does not automatically means that my closest pair of the whole region will either be this or this. It may not happen. It may be some other point here. Maybe some other point is here, such that they are the closest pair. Actually, it may so happen. So just getting these and these and then comparing among these two closest pairs, it does not lead the solution. Okay, so that we should be careful about. And the second important thing is normally we will show that we provide one solution where we claim that this Fn is actually of the order of n. Okay, or some you can think of so when this is order of n, then only you can claim that this has a solution actually order of n log n. Basically. If it is Fn is 1, then this solution will have actually logarithmic time, which is we actually cannot make for this particular problem. We cannot make Fn equal to constant. We cannot. Probably with some argument we can claim that this is possible. It is easy to show this is possible because now this On square it is easy to show that this is On square, because this is, if we just apply trivial algorithm, then we get it On square, and in that case overall actually it becomes something like overall n square. Okay, this solution becomes like this. So today we are running out of time, so we will that the main crux of the problem, okay, is how to show that the Fn is actually of the order of n. How the joining can be done in order of n time. Just like in merge sort, you might know the idea is actually recursively I sort the first half and recursively I sort the second half. That essentially means somehow I have sorted the first half of the array, somehow I have sorted the second half of the array, and then I merge. There is a merge procedure. I merge them in such a way that if you give me two sorted arrays, my merge procedure will give a new sorted array, okay, which comprises all the elements of these two subarrays, okay, and it can be shown that the merge procedure can be done in linear time. Once it is done in linear time, that's why merge sort becomes n log n. Okay, so just like that, here we divide it approximately of equal size, and then we show that the margin here it is not the margin of merge sort, it is some special kind of margin we need, and that can be done in order of n time. We will see that. Okay. So, okay, fine. So this is the problem we will discuss in the next class. Okay. If you have any further questions, you can raise. Okay. Okay. So, we will take up the problem in detail in the next class. Uh, Yes, let us have a very short meeting. Okay, just maybe 5 minutes. Okay.